Copper staves have replaced traditional cast iron linings in modern blast furnaces due to their superior cooling performance and extended campaign life, often exceeding 20 years. Yet, a curious phenomenon appears, that is, about a measured stave temperature are lower than expected. Interpreting these readings accurately is essential, and this study aimed to build a thermal model that link temperature pattern to furnace condition, ultimately improving lining management and process reliability. Now, our primary goal is to understand a stave temperature behavior using a thermal model. Why does this matter? Because temperature trend reveal the unseen conditions inside the furnace, such as wall wear, gas flow anomalies, or accretion behavior. Accurate interpretation helps us stabilize operations and extend campaign life. It's not just about reading number, it's about reading the furnace correctly. Hence, let's explore the evolution of stave linings. In the past, cast iron stave were the norms, robust but limited in heat extraction. Modern blast furnaces use copper staves, offering very high thermal conductivity, enhanced cooling power, formation of a protective accretion layer, longer operation life up to 20 years and more. This upgrade changes how we interpret thermal behavior. Now, stave temperature are more than just readings. They are the furnace's vital signals and signs. These temperatures are influenced by many phenomena, and few highlights of them are as follows: accretion formation on a stave surface, gas flow distribution inside the shaft, material descent along the wall. If we read this pattern correctly, we can detect instability, wear zone, and process disturbances very early, well before damages occur. The most important part is to read these trends correctly. Now, coming to the four typical thermal state that are that we observe at the stave hot phases, and out of them, noble or stable operation with uniform gas and material flow accreted a frozen layer of slag or ore on the stave face, acting as a thermal insulator, attenuated poor gas flow due to fines buildup on restricted permeability near the wall, channeling hot gases bypass the pack burden, leading to localized overheating. Each condition leaves a thermal signature and tells us something about what's happening inside, and that's why this is most important to read each one trained with a right logic and science. So as we can see that thermocouple embedded in the staves offer a rich diagnostic insight. here how their reading align with the different condition. For example, accretion, low temperature, very stable, indicate physical shielding, whereas attenuation, also low temperature, but moderately unstable. That is, if you see both lines, one line must be very stable, flat, but the attenuated line must be zigzag and fluctuating in nature. Of course, it will be also lesser quantum or lesser intensity, but with a more stability, but fluctuating, slight fluctuating, but moderating. Okay, now and once we come back to channeling, then we see that sudden spikes, high risk for a stave wear. Whereas a normal, if we talk about normal, then we can see it is a safe range fluctuation, ideal operating zone pattern. Recognition is key to proactive process control that we have learned from all these four profiles. Hence, we need to understand each trend, each line, each graphical trend correctly. What it means, and then its relation on the process part will be much easier, and we take a right action to take care of each anomaly situation, and then by doing this we can enhance the right decision. uh, this brings the steadiness of the process, and eventually it will help in meeting the more higher campaign of the furnace, or we can say the copper coolers. Now coming to the thermocouple behavior that we have seen here, just discuss in the just finished our slide, and here is the most important part which confuse most of the time. This is about a accretion and attenuation. Now let's compare two deceptively similar state. Accretion is basically a physical layer formed on the stave, protective, stable, desirable. Whereas attenuation, it is caused by fine particle disrupting gas flow, not physical, less stable, both result in low temperature, but misinterpreting attenuation as accretion could lead to delayed response or false assurance. That's why it's very important to differentiate both in order to take corrective measure. Now coming to the four process state, our model highlight four distinct state as we have studied in the last three slides almost, about a normal, accreted, attenuated and channeling, and each trend need to be read correctly by the operator. Now each condition reflects a different combination of heat load, gas flow and material descent near the stave. This classification helps us to decode thermocouple pattern into real-time process insights and turning this thermal data into operational intelligence. So modeling approach has been also applied in this direction of analysis, and to analyze this condition, here we use finite element analysis to develop a 3D steady state thermal model. Input include thermocouple reading and thermal properties of a stable material. These simulations allow us to map observed temperature to actual furnace scenarios, making interpretation more reliable and more predictive. Now, as accreted steps show low and very stable reading, attenuated zones also show low reading but slightly fluctuate due to shifting lines. Channeling zones show rapid spikes as we have already discussed, And these channeling zones are basically high temperature danger zones. Surprisingly, attenuation dominate more than 90% of the time. It is a silent disruptor we must manage carefully. And thus, the impact of attenuation goes beyond temperature reading, and it is all about a prevention and cure. So we can say that it can prevent accretion layer formation, delay reduction reaction near the wall, and it lead to cold descent of unreduced burden. So we must monitor and adjust wall burden composition to minimize the effect and maintain the campaign. Hence, to detect attenuation early, look for the suitable indicators like slightly unstable low temperature reading, minor spikes followed by quick cooling, gas breakthrough events, wall side temperature lag despite central heat increase, unusual temperature asymmetric between adjacent steps. This is also one of the very important clue. And in order to correlate all this clue, allow timely correction before damage occurs is the right approach to operate the furnace properly. So, in closing, we can say that copper steps have transformed blast furnace cooling, but interpreting low temperature is not always straightforward. Attenuation and accretion both show low reading, yet only one offer protection. Though thermal modeling and careful thermocouple analysis we gain insight into near wall condition and unlock proactive control strategy. So the final takeaway, as we can say that remember, a step temperature is the language of the furnace. This study helps us translate that language into actionable strategies. Aligning, monitoring, modeling, and modern design with a step behavior will drive longer campaign undoubtedly. It will also have a safer operation and